Thank you for this opportunity to talk about the work that we've been doing with network function virtualization and its application to 5G and beyond. This is work that's being done with my students and is also enabled by our collaboration with Tim Wood's group at George Washington for OpenNetVM. I want to make the case that while 5G cellular shows great promise for enabling new applications with the introduction of new radio, it's equally important to address system and network protocol issues to achieve that promise. So NFV has become commonplace in the last few years. The main idea behind NFV is that we want to run functions in software that were traditionally implemented in hardware. This trend has been enabled by a number of factors, system capability, and so on. So this has enabled network resident services as well as faster evolution of the functionality of the network. In fact, a couple of years ago, AT&T said more than 55% of their functions had been virtualized. In 2014, we had developed an open source NFV architecture that we call OpenNetVM. Its hallmark is the high performance achieved for packet processing and its scalability. NFs in OpenNetVM run as containers and are managed as using an NF manager. OpenNetVM fully exploits the capabilities of DPDK with NFs that run in user space. And the main features we had were, one, we wanted to deliver data to and between NFs with true zero copy. So the CPUs are not doing the work of moving packet data within memory. Using DPDK's pole mode driver, we've eliminated the overhead of interrupts. It's very careful in being aware of non-uniform memory access. Receiving and transmission of packets are performed in receive and transmit threads in the NF manager and can be scaled as needed to meet packet processing requirements. And we ensure complete lock-free operation for each NF, as it has its own RX and TX rings for packet descriptors. OpenNetVM can support forwarding throughput of about 60, 70 gigabits with just a small number of cores of conventional Intel CPU with base forwarding latency of less than about 10 microseconds. And we can start an NF in less than half a second. And it's been available as open source for a while now, and we have a good number of users and a good number of students actively working on OpenNetVM and providing support for users. We've started introducing support for also GPUs and SmartNICs with OpenNetVM as well. So this slide shows how packets are exchanged between the NF manager, which acts as a demultiplexer of packets, and the NF. We've done a number of things very carefully in OpenNetVM. One of them is to ensure true zero copy packet delivery. Packets are directly DMA'd into shared memory with the application running in the container, receiving a reference to the packet from the packet descriptor that is shared between the NF manager and the NF. And packet content can then be manipulated by the application or the NF running in the container. We can extend this to service chains, obviously. A service may be built by pulling together a complex set of NFs together. There may be multiple paths, and the packet routed through the NFs it can be routed in a state-dependent manner or something even more complex. And it's important to do this efficiently with packets being moved through the chain efficiently. And so the key is to make sure packets don't get copied from one location in the memory to another, and applications in OpenNetVM pass packet references to other applications through the descriptor ring, and only one application has access to a given packet at any time for writing. So we completely avoid locks. We're able to run on a relatively small server, typical HTTP traffic close to 70 gig. And this has gotten faster over the years with faster machines, with more cores. But we wanted to demonstrate the feasibility of having a low cost off-the-shelf server acting as a software-based edge forwarding node so that we can have it act like a bump in the wire. And we've done a fair amount of work in the last few years in providing support for GPUs, virtualizing the GPU, supporting SmartNICs, virtualizing that, and so on. But now what I want to do is talk about the work we've been doing in using this NFV platform for implementing what is a packet core for cellular network that runs on the other side of a backhaul network and is responsible for most of the control of data flows to the user device through the base station. If you see what is involved on an end-to-end basis, we used to measure the latency for LTE to be of the order of 50 to 100 milliseconds. All the pieces, radio, mobile core, and the network cloud components, all of these end up contributing to the delay. And getting that down to 1 or 10 milliseconds can be a challenge. And if you look at latency, architecture ends up being the main driver. And there isn't really like one silver bullet. You need to carefully consider all the protocol layers. You guys are all doing a great job with new radio efforts and so on. The focus for us has been the mobile core. And of course, there's other things that we can do on the edge cloud as well. This is, I'm just reusing this for emphasis from LTE. And this is where we started when we started working on CleanG initially, which was to say, how can we use NFV in the context of cellular, going especially from LTE to 5G and beyond. And our focus is on what is called the EPC, which comprises in the LTE context SNP gateways, which act as an Ethernet switch and a packet gateway, as well as a mobility management entity, all of which are typically housed in a data center on the other end of a backhaul network on the way to the core network and the internet. Multiple eNode Bs get connected to the MME and the SNP gateways with many mobile devices supported on each eNode B. So if you look at this cellular EPC design, it has evolved from the way cellular networks have been traditionally built, separate purpose-built hardware appliances for each function, and scalability considerations like with these appliances end up needing separate data and control plane components. And this brought about a need to make sure that state is kept consistent across all these components, for which they designed a fairly complex control plane protocol. So one of the key aspects of the LTE control plane is how mobility is handled, and the communication between mobile devices like the UE and the P gateway for connection onto the IP network is over pre-set up tunnels. And that's how we've always traditionally dealt with mobility until Dipankar and everybody else started working on mobility first. But the tunnel is set up, and that is orchestrated by the MME and has to be changed every time the UE moves from one eNode B to another. And the new tunnel is set up before the previous one is torn down, make before break arrangement. Tunnel setup also occurs when UE goes down, goes from idle to active, not goes down, which it may do frequently to conserve battery power. That's all good, but what's the consequence? There are fair amount of difficulties with having these tunnels beyond just the complexity of the protocol, which we'll soon see. There's a significant amount of state that has to be maintained in the EPC, since each UE has one or more distinct tunnels to be established. And the cost of the state becomes a concern as we scale up to very large numbers of UEs with the ongoing deployment of 5G. and especially when you go to IoT devices and others that are being integrated into the cellular network. So let's look at what happens when a UE is handed off from one eNode B to another in LTE. This results in about 33 control messages in total, which can be a lot of overhead, both in messaging, and it also takes time. When you look at the other events in a cellular network, like an initial attach, or more importantly, the one that I concern myself, especially when you have devices connecting to the network, is idle to active transition. And those also consume a lot of messages. And this was with LTE. And the overhead for an idle to active transition can end up being serious if these devices frequently try to conserve battery power and go idle. So maybe 5G is a savior, but if you look at what happens with 5G, the protocol is no different. The overhead is similar, if not a bit higher. If you look at, let's say, handover in 5G, and the reason I'm going over this is to see that, all the partitioning that they've made, I've actually gone through it in a more simple fashion, where when a UE moves from a source base station to a target, you'll see the complexity of it. The UE needs to send a report back to the source G-Node B, especially signal strength measurements. And that causes the source G-Node B to decide a handover is needed. And the initiated process results in a number of messages being exchanged between all the different components in the EPC. And the second G-Node B has to set up a new tunnel with a tunnel ID. And that has to be done in a coordinated manner across the AMF, SMF, and the UPF, with the AMF orchestrating the whole process. Eventually, everyone has the tunnel ID they're supposed to use, and this results in what they call the preparation phase being complete. In the execution of the handover, the command is provided through the G-Node B to start the handover to the UE. And the UE syncs up with the target G-Node B. And the important point is to remember that the data plane for the session is held up for completion of the control plane action so far. After this, incoming packets are redirected through the source G-Node B to the UE. While at the same time, all the components know about the progress of the handover, and new arriving packets go through the direct path to the target G-Node B. And they have to be buffered there until the last data packets are drained from the old indirect path. They use a end marker for that. And when the end marker arrives, then buffered packets can be delivered to the UE so that all the packets are in order, right? The old association, that is the GTP tunnel with the source G-Node B, can then be toned down, and everyone can clean up old state, and radio resources are released. And so finally, this handover is complete. The point of going through this so painfully is that there are so many messages exchanged. And there is certainly a logical reason for every one of these messages, but that is only if you take as a given that these are separate, distinct EPC components. When you move to an NFV environment, not only do you have a chance to rethink the system and network architecture, which people are doing, but you can also start thinking of what are the correct protocol exchanges needed. You don't truly really get the advantage of NFV until you grab hold of the opportunity to think holistically of both the architecture and the protocol. And if you say, look, in the future, we are going to go to smaller cells, and the efficiency of these control plane protocols will then end up becoming even more important because you have more frequent handovers with IoT devices using cellular connectivity, small packets, infrequent communication, with frequent transition to idle to save battery power. All of this will need the control plane control plane to become more streamlined. So the move to having a virtualized EPC is already happening, if it's not already happened. And that's a good thing because it provides more flexibility and can also help with scalability. But just implementing the same set of protocols will mean an enormous opportunity being lost. A software EPC that can support a large number of Gnode Bs, we can take advantage of the scale to in fact derive several efficiencies, reduce a lot of the mobility related complex interactions, especially when it comes to GTP tunnel establishment and teardown. So we've been working on a design for a new architecture that we call CleanG for the cellular packet core, both from a system architecture as well as a control plane protocol perspective. One of the primary features is that rather than going towards the disaggregation of components, which is what seems to be the trend, we see that rather than having them reside on different nodes, we seek the consolidation of the EPC components to still provide deployment flexibility and scalability. And we can get much higher performance, especially in the sense of latency. More importantly, we recognize that there's an opportunity to rethink the control plane protocol that reduces the number of these control plane transactions and leverages the fact that NFV-based systems can simplify a large amount of unnecessary messaging we see because of these different functions not being co-resident. So with our architecture, what we've done is we've implemented the EPC as a consolidated set of NFs on a system which can run on an NFV platform like OpenNetVM. We break the EPC functions into control and data, not unlike what people are thinking about, but not taking control and data components that they traditionally had in one unit and breaking them up into separate NFs. With the shared memory framework with OpenNetVM, we can minimize the latency between control and data plane. But the shared memory is not the only aspect we focus on. NFV gives us an opportunity to quickly and dynamically adapt its resource allocation based on the relative proportion of control and data plane demands, which is an important benefit going into this virtualized software-based environment. What we feel is more important is the opportunity that this infrastructure provides for protocol improvements. So we developed a CleanG control plane protocol that reduces the number of messages significantly because of the consolidation. We see several places where we can merge a number of functions that otherwise required multiple messages between distinct components. And in some cases, we could reorder message sequences that also reduce the number of messages. But importantly, we retain key functionality of radio resource management and security. Here's one example of idle active transition, the control plane messaging that is needed with CleanG. We reduce it to about 8 messages compared to the 13 or 14 we saw with LTE and with 5G. And when we look at the handover protocol with CleanG, we're able to complete it in about 10 messages compared to the 25 or more messages that we see with 5G. So if you look at the performance that we see with CleanG in comparison, we did this with LTE, so the performance that we see with 5G is not that dissimilar, but I'm showing the things that we showed with LTE. For individual control plane operations, CleanG is about a factor of 2 lower in latency. We did an apples to apples comparison with even the LTE components being co-resident on the same OpenNetVM node, so that both CleanG and LTE get the same benefit of internal data sharing. Our implementation captures the essentials for the message exchanges, even though all the internal operations are not completely implemented. We are working on also an apples to apples 5G open source implementation on OpenNetVM so that we can demonstrate the same kind of performance improvement. When we scale up in terms of number of users, we again see that CleanG scales better with increasing load because of the fewer messages and less queuing. And this is especially true for events like handover and attach. Another important consideration is the impact of the control plane on the data plane. Data packet forwarding often has to be buffered at the EPC until the control plane action is complete. And when we scale up, we see that there is a big improvement in the data plane latency, especially median and tail latencies are a lot less with CleanG. So in summary, moving to a software base means that, going to NFV-based implementations are becoming common with cellular EPCs as well. And what we've shown is with our CleanG work that a holistic solution that goes beyond just using a software platform, but also looks at the protocol can offer significant benefits for cellular. And so we see considerable value both in refactoring the network components and the protocol enhancements at the same time for us to truly get the benefits of NFV for 5G cellular networks and going beyond. I wanted to put in a plug that you can get our OpenNetVM source from our GitHub repository here. I'm done. Thank you very much for your time. Happy to take questions.
Thank you very much, KK. So I have a question, and I was starting to type it in the chat, but I'll say it.
Yeah.
So if we push CleanG to the extreme, right, is it possible to collapse the whole control system into a single instance or single, I don't want to call it VM, but virtual function? Would that make sense?
So what we've looked at to do, Ivan, is understand what pieces need to be distinct from a control versus data perspective. And in a sense, there's, by doing what we are doing here with exploiting shared state between those two components, we see no reason to then further consolidate them together. And the reason I say that is you want these to scale somewhat independently, right? Depending on the kind of workload that you're supporting. And maybe even, you might end up having multiple physical nodes, but you can have them supporting different APNs, for instance, and you can then have those have different characteristics of workload that they need to support. So you can scale more data NFs in one, more control NFs in the other. So I do not see a fundamental reason for consolidating them further because there's not a lot of protocol going back and forth in our approach. Okay, if you look at the 5G way that people are doing it with using, HTTP and REST and so on, that's a different issue. But in our case, we don't see going in that direction. As a result, we can see very simple interactions between the core and the data. I mean, the control and the data plane.
Yeah, control. Okay, so
Ivan, can I ask KK something?
Of course.
I just wanted to say, KK, that thank you for the talk, and also that this code could be quite useful for Cosmos experimenters who are trying to build 5G networks or doing applications work.
Yes.
So at some point, we should coordinate making this into a package that's available in our library.
Yes, and that is my goal as well, Dipankar. This last about 9 months, from right around March when I got stuck at home, we've been spending most of our time working on a 5G implementation as well to do a apples to apples comparison. And that's taken a lot of time with just a couple of our students. and we are now collaborating with some folks from NCTU as well on their free 5GC implementation to put it on OpenNetVM. And we've learned a little bit from that also, because we now are bringing back some of the learning from there to make our CleanG EPC implementation more robust and complete. Sorry, go ahead.
Yeah, that's good. So whenever you're ready, we lost 6 to 9 months as well. So I think we can wait and we can take what you have. I think in a few months, I'm expecting this type of usage to pick up, because many people have approached Cosmos about doing application level experiments. So a 5G package would be great.
Yeah, okay. I will take that under advisement and make sure that we make it at least what we have robust enough for others to play with.